Hey everyone, welcome back to Syntax Grid. In today's video, we're diving deep into the full code implementation of logistic regression from scratch using NumPy and Pandas. We'll cover how logistic regression works, implementing it from scratch without relying on any built-in ML libraries, training it on synthetic data, evaluating its performance with accuracy and visualizations. You'll have a solid grasp of how logistic regression actually works behind the scenes. So, let's get started. 1. Importing required libraries. NumPy. Used for mathematical operations, especially matrix operations. Pandas. Helps in data manipulation. Matplotlib PyPlot. Used to visualize the cost function and classification results. Sklearn model selection, train, test, split. Splits the dataset into training and testing sets. 2. Sigmoid function. The sigmoid function is the core of logistic regression, converting any real number into a probability between 0 and 1. This function ensures that predictions are in the range 0, 1, making it suitable for binary classification. 3. Cost function and gradient calculation. The cost function is based on binary cross-entropy, log loss, which measures the error between predicted and actual values. The gradient is the derivative of the cost function, used to adjust weights during training. Here, XTD ensures correct dimensionality for matrix multiplication. 4. Training logistic regression using gradient descent. Initialization. The model starts with all weights set to 0. Gradient descent. Iteratively updates weights using learning rate alpha. Controls the step size for weight updates. Epochs. Determines how many times the algorithm updates the weights. Cost history. Stores cost values for visualization. 5. Prediction function. Uses the learned weights to make predictions by applying the sigmoid function. Converts probabilities to binary values, 0 or 1, based on a threshold, default 0.5. 6. Generating synthetic dataset for binary classification. Creates random feature values using a normal distribution. Defines a nonlinear decision boundary. This ensures a roughly balanced dataset. 7. Adding bias term, intercept, and splitting data into training and testing sets. Adds a column of ones to the dataset to represent the bias term. This allows logistic regression to learn an intercept instead of being forced through the origin. Uses an 80-20 split to train the model on most of the data and test its performance on unseen data. 8. Training the model with hyperparameters, learning rate, 0.05. Higher rates can speed up convergence but risk instability. Epochs, 2000. Higher values allow better convergence but increase computation time. Trains the model and stores the cost at each iteration. 9. Making predictions on test data. Applies the trained model to test data. Uses the sigmoid function and thresholding to classify each data point. 10. Evaluating model accuracy. Compares predicted values with actual labels and computes accuracy. 11. Plotting cost function over epochs. Visualizes how the cost decreases over time, indicating model improvement. If the cost flattens too early, increasing epochs or adjusting the learning rate may help. 12. Scatter plot of predictions. Displays a 2D scatter plot using two features. Colors indicate predicted class labels, helping in visually understanding the decision boundary. And that's a wrap on logistic regression implementation. If you found this helpful, make sure to smash that like button, subscribe to Syntax Grid, and hit the notification bell so you never miss an update. Drop a comment if you have any questions, and let me know what topic you'd like me to cover next. Until